Okay, so hello everyone and welcome to my talk about Xenpwn, breaking para-virtualized devices. Before I start with the actual interesting content, I have a short introduction about myself. So my name is Felix Wilhelm, I'm a security researcher at ENW Research, which is a German company, as Dave already mentioned. My main focus lies on application and virtualization security. And in the last month or last year, I mostly concentrated on security appliances on the one hand side. So we had some research on FireEye, which got a bit of legal and a bit of media attention as well last summer. And just recently I looked at the Palo Alto next generation firewalls. And the second area of interest is hypervisor security, and I mostly look at the Xen hypervisor in the last months. And that's also the topic of today's talk. So shortly about the agenda. I first want to introduce you the concept of device virtualization as well as para-virtualized devices. So the topic of the talk is breaking para-virtualized devices. So of course I need to give you a short introduction what a para-virtualized device is. And then we talk about the concept of double fetch vulnerabilities, which is a vulnerability class I used to, or I looked for in para-virtualized devices. And I did this using a tool I call Xenpwn. And I will present the architecture and the design of the tool and give you a short introduction or a short overview about the different results I collected. And then in the second large part of the presentation we do a case study and I show you how we can exploit one of these bugs I find very interesting. So it's not the most critical bug in a real world environment, but from a technical background it's very interesting, at least I think so. And we go deep dive into the exploitation of this one. So let's start with device virtualization. So basically you have the problem virtualized systems need access to virtual devices. So that can be disk, network or serial devices or something like this. And traditionally hypervisors or virtual environments use device emulation to support this. So the core idea of device emulation is simply you have this really old and well supported hardware device that has driver support in every operating system you can imagine. And you emulate that in software, and this has the advantage that your guest operating system doesn't need any special drivers. You can simply install it in the virtual environment with standard installation sources, and it will work out of the box. So the screenshot on the left is actually this floppy disk controller Jason Gaffner from CrowdStrike looked at in the Venom bug. So this was a classic vulnerability you will often find in device emulation. So emulating some old hardware device in buggy code. Now the problem with emulated devices is on the one hand side they're kind of hard to implement securely and correctly. So if you just look at QEMU, you will see hundreds of device emulation bugs involving memory corruptions and all this stuff. But even if you don't look at the security of them, they're kind of impractical because they're really slow. So the performance is really slow and you don't have any support for advanced feature you might want to have in your virtual machine. Because you're emulating a device from the 90s, of course you don't have access to any advanced features of a device that might be released like this year. And the slow performance is mainly because you do something like memory mapped I/O or port-based I/O, which will trigger the M exit for every data transfer, which is really slow. And you don't want to do this on production machines. So every of the main hypervisor vendors decided on implementing para-virtualized devices. And para-virtualized devices are simply specialized device drivers that are implemented to work in a virtual systems. So they know they are virtualized, they don't speak with real hardware, instead they communicate with the hypervisor or the management domain in some kind of way. Emulated devices are still supported, and that's still why you see a lot of security vulnerabilities or advisories talking about emulated devices. But if you look at the actual usage in a modern virtualized system, they are only used as a fallback mechanism, so for installation or during boot up. But if you then look at how the virtual machine talks to these devices, it will always use the virtualized devices. And this is the case for all major hypervisors. So I mainly looked at Xen, KVM, Hyper-V, but it's also true for VMware, for example. Now, para-virtualized devices, and this is where it starts to become interesting, are all implemented using a split driver model. So you have this front end, and the front end runs in the guest system. It's simply a device driver that runs in the guest kernel. And the back end then runs in the host system or the management system. So on KVM it would be the host system, so the host Linux system. On Xen it would be running in the .0, so in the management domain. And so they name these components differently. So front-end and back-end is like the Xen terminology, but you also have the virtualization service clients and virtualization service provider in Hyper-V, and you have weird I/O devices and drivers for KVM and also for VirtualBox nowadays. But if you actually look how they are implemented, these implementations are quite similar. The core idea of all these parallel-virtualized devices is that they're implemented on top of shared memory. And shared memory is a great idea for this because it has really great performance, so you don't need to do like any nested parsing or a lot of copies or something like that. You simply write into memory and it will be, or it can be used on the other side. It's also really easy to implement. If you have a hypervisor, or sharing memory pages between different execution contexts is like a core feature of these hypervisors. So implementing a shared memory message mechanism on top of that is really trivial. And then you have more advanced stuff that's possible if you use shared memory. So for example, an idea is zero copy algorithm. So if you pass through a network card to a virtual system, for example, you can do zero copy algorithms, which means the data is directly written into the DMA of the network card, or something like that. And if you compare modern hypervisors and compare their performance, so modern hypervisors that use hardware-assisted virtualization, you will see most of the differences in performance are actually performance difference in these virtualized devices. So this is like an area where everyone spends really a lot of time or a lot of development effort to make these devices as fast as possible. Of course, if you have a shared memory page that doesn't give you directly like a high layer protocol, you can use to talk between these components. But all these vendors simply implement classic ring buffers on top of this shared memory to allow like parsing of requests and responses. Some of the vendors have like these shared memory mappings created constantly, or these mappings are constant, so this means the virtual machine boots up, the driver initializes, some kind of shared memory mapping is initialized, and this stays constant for the whole lifetime of the virtual machine. Other vendors, for example Hyper-V, create these mappings on demand when you transfer a large amount of data. So why are parallel-virtualized devices interesting from a security perspective? And the main reason for that is, of course, that the backend runs in the privileged context. So it runs on the host system or in the management domain, which means the communication between the front end and the backend is a trust boundary. And then you have all the typical low-level code, so all backends are implemented in C, of course, for performance reasons. And you have protocol parsing. And this is something I think a lot of people don't recognize. It's more or less the same, this whole protocol stack has the same attack surface as normally like a network protocol or so. So everything that's passed in the back end is exactly as critical as like a network daemon running on a privileged system. And of course, if you combine low-level code and protocol parsing, you will have a lot of bugs. Interestingly, not that many bugs are actually published in these code paths, so that speaks for the quality of the back-end code, or that not that many people are looking at it. But there are a couple of examples. For example, there was a heap-based buffer overflow in the KVM disk backend. It was released sometimes in 2011. And just last year, they had a buffer overflow in the Hyper-V storage backend, which was interestingly discovered by a Microsoft researcher, and he was actually credited in the advisory, so that I think was the first time Microsoft credited an internal researcher for a vulnerability. So that's quite an interesting bug. And it seems to be the case that these parallel-virtualized devices are not as much researched as emulated devices. So everyone has written a fuzzer for like emulated devices or looked at the QEMU source code. but not that much research is published on these para-virtualized devices. And the reason for that is mostly that all the protocols spoken between the front end and the net and back end are device and hypervisor specific, so you have to do a lot of work for each device and for each hypervisor you want to audit. And this whole stuff is kind of hard to fuzz, because you have a lot of state involved, and for example, if you start fuzzing your disk backend, if you send invalid message, for example, Xen will simply turn off your virtual machine, which might even corrupt like your disk image of your virtual machine, so you might not simply be able to reboot and start fuzzing again. So fuzzing this stuff is kind of complex, or especially more complex than like simply booting up a live CD and fuzzing memory mapped I/O or something. Okay, so in addition, I think it's a very interesting target. Nowadays, device emulation is most often done in user space. So if you look at like QEMU is simply a user space process that's running on your host system, and nowadays it's most often heavily sandboxed. So you have like SE Linux and I don't know, additional sandboxing. On Hyper-V, the VM worker process is also a user space process responsible for the device emulation, and it's sandboxed using all the standard Microsoft Windows operating system mechanisms. In contrast, many of these para-virtualized backends are implemented in the kernel. And the reason for that is simply higher performance. So if you look at the disk or network backends, they will be implemented in the kernel space. So the backend components are simply kernel modules or kernel drivers running on the host system or in the management domain. And of course, this means that if you compromise such a backend, or if you find a vulnerability in these backends, then you have like an instant win because you're running in the most privileged context in the management domain. So it's game over. It's like, these are the bugs attackers are really interested in because you don't need an additional sandbox escape. And then you see that para-virtualized devices are also becoming more and more important. So all the vendors support more different device types. So nowadays you have like support for PCI pass-through. You want to support virtualized touchscreens, for example, for desktop or laptop systems. You have acceleration in your virtual machine, and all this stuff is implemented using the same mechanisms as the classic para-virtualized devices. And if you look at the code base, it starts these stuff doesn't get easier, so they add more features and more optimizations to increase the performance. So it's not like this is legacy code, they add new features with every release, making it a kind of an interesting target. And then you have future development, which you can see in Hyper-V, for example. The vendors start to realize that device emulation, so the classic mechanism of device emulation, is kind of hard to secure, so they start to remove support for emulated devices. So if you have a Hyper-V hypervisor and use a generation 2 virtual machine, so at the moment this can only be a Windows virtual machine, but it doesn't have any access to emulated devices anymore. Instead, it completely relies on these para-virtualized devices. So in a couple of years, device emulation bugs will probably not be usable in a lot of environments, and instead you have to attack para-virtualized devices. So this whole stuff was part of my master thesis basically, and my goal for this was I want to find an efficient way to discover vulnerabilities in para-virtualized devices. And if I mean efficient way, it shouldn't be like completely manual, so I'm not like the biggest fan of doing in-depth source code analysis of these backend components or binary reversing, because when you look at a proprietary hypervisor, you don't have source code for the backends available. So I wanted to automate it in some kind of way. And the core idea of the thesis or of this work is basically you don't see any published research if the use of shared memory affects the security of para-virtualized devices in any way. And of course there's a bug class that only affects shared memory interfaces, and that is the double fetch. So a lot of you will already know what a double fetch is, but I have a couple of slides to introduce it again. So a double fetch vulnerability is simply a special type of time of check to time of use bug that affects the shared memory interface. And like the really simplified definition is you have a memory address, and this memory address is accessed multiple times from a privileged context, but validation of the fetched data is missing in at least one access. And like this vulnerability class or this vulnerability primitives allows you to put it like simplified, you can bypass a certain check. And after you bypass this check, you might gain a lot of different kind of vulnerabilities. You know, as we will see, you have like arbitrary read writes, buffer overflows. It can even give you more or less direct control over the instruction pointer. So it's a kind of a very interesting bug class. So I published a blog post at the end of last year about this stuff, where I had like a short history segment, and I was directly corrected by by Spender from GR Security that I missed a couple of references. So I'm hopeful this is like kind of correct, but if I'm missing anyone important, I'm sorry, and please come back, come to me and remind me of that. So the term double fetch was coined by Fermin in a blog post in 2008. So this was the introduction of the term double fetch, but the bug class itself was well known before that. And most of the first part of the research talking about double fetch was published in 2007, 2008. So at Usenix you had a paper named Exploiting Concurrency Vulnerabilities in System Call Wrappers by Robert Watson. And at the Chaos Communication Congress in 2007, Twiss and Estra Q published research about that. They also published this well-known FRAG paper about Linux kernel exploitation, where they also talk a bit about race conditions and this bug class, later known as double fetch. And the bug they used to talk about this is the send message Linux bug, which was reported in 2005. So this is like the earliest example I could discover that really used this kind of vulnerability. So this is the simplified code how the send message bug worked. So this is basically code you can reach when you do the send message syscall, and you can see in line 5, so the first line, you have this get user call, which copies a value from user space into the UCM-len integer variable. And this variable is then used to calculate a memory allocation size. And later on, you have a second call to get user, where the UCM-len is again copied from user space and is then used as a size argument of a copy operation. And of course, this is trivially exploitable if you just flip the value between these get user calls from like a really small value to a really big value, because then you have a classic heap overflow. I think there are public exploits available for this to trivially exploit that to gain privilege escalation. So this is like the first bug that fits this description of double fetch vulnerability. So, and then in 2013, you had this really interesting research identifying and exploiting Windows kernel race conditions via memory access patterns from Yorgu and Gimbal, also known as Xenpwn. And the idea was they extend the box CPU emulator to trace all memory accesses that are performed from kernel to user space, and then search these memory access traces for potential double fetch vulnerabilities. So they look if the kernel accesses a user space address multiple times in a row. And they used Xenpwn, and they discovered a significant number of Windows bugs, so like local privilege escalation bugs in the Windows kernel. Also won a well-deserved pony for their research. But interestingly, nobody really followed up on that. So they published their white paper, they published the open source, so they basically published their whole code. But nobody used it for like different targets or something like that. And in addition to their research involving the code release and the vulnerabilities they discovered, they also have a detailed analysis how exploitable these double fetches really are in practice. Because you have like a race condition between these two accesses, and what's the chance to successfully exploit that if you have like a really small race? And to summarize it really quickly in like one sentence, if you have a multi-core system, so your virtual machine, or in this case the Windows system has like 2 cores at least, then even if your race is extremely short, like only 2 or 4 instructions short, these vulnerabilities are exploitable. And as the name of my talk suggests, of course, Boxdown is the main inspiration for this research. So the core idea was basically to use the approach from Boxdown, but targeted against these para-virtualized device interfaces. So this is another example of a bug found by Boxdown. It's in the Windows kernel anti-app help cache lookup entry function. And you can see in line 1, so the EDI register points to a shared memory location, and they access a value at x18, put it in ECX, and push this as an argument to provoke for write, which basically checks that this is a pointer to user space, so it should not be possible to override an arbitrary kernel address. So this is like the destination for a memory write, and they use provoke for write to make sure it's a valid user space address. And directly afterwards, they call memcopy and try to use like this the same value as the destination of memcopy. But as you can see, they don't reuse the ECX register. Instead, they fetch it from memory a second time. And again, if you can switch the value between line 1 and line 9 in this code, you can override an arbitrary memory address in kernel, giving you privilege escalation. The interesting point about this code sample is, of course, we don't have the source code for this, so you can't actually be sure how this looks like in source code. So for the send message bug, the bug was pretty easy to find by looking at the source code because we had these two invocations to copy from user. In this case, it could be an optimization done by the compiler, so you just have like a pointer. The pointer could be dereferenced multiple times in the source code, or it could be a compiler optimization. So as we'll see later on, this is an interesting aspect of these double fetch vulnerabilities. So Xenpwn, as I said before, the main idea is we want to adapt this memory tracing approach that is used by Boxdown, but uses for analyzing para-virtualized device communication. Now the question might be, why do you not simply look at, simply use Boxdown? It's open source, so I could just use this to look at it. But Boxdown, for this use case, it has a couple of problems. So first of all, it's like extremely slow. If you ever use the Box CPU emulator, you probably notice it's slow by default. So it's just software emulation, so it doesn't have any acceleration. So even just booting up a modern Windows system takes a long time. And if you enable Boxdown, so if you enable this tracing, then it slows down by a factor of 5 or more again. So it's not really usable for complex environment. And the main problem of this is that this is passive overhead. So every memory access is slowed down, while we are only wanting to trace like memory accesses to these shared memory pages. So we are not interested in all memory accesses that are performed by the whole system, but only in a really small subset of that. And this makes this really gigantic passive overhead of Boxdown quite a hassle for us. Then you have the problem that, so this is not a problem of Boxdown, instead it's a problem of Box. If you have the newest Windows Server version on 64-bit and you want to run it in Box, it will simply crash and show you a blue screen. So Box is not perfect in emulating current versions of 64-bit operating systems. And then I have, this is also a problem they introduce in the white paper. Basically, you simply the approach of dumping like memory traces to a text file does not really scale if you want to produce really long traces. So one of the main problems is actually they write so much to text file that the disk I/O is like heavily used. So my idea, go away from Box and instead implement this memory access tracing based on top of hardware-assisted virtualization. This is like the core idea or the core architecture of Xenpwn. The core concept is nested virtualization. So we have this level 0 hypervisor at the bottom, and our target hypervisor or the software we want to look at is this level 1 hypervisor, and it runs as a virtual machine under our level 0 hypervisor. It then has two virtual machines, so the management domain as well as the unprivileged guest. They communicate using the front end and the back end, and the box is in green, so this is the communication we actually want to look at. And all our software, so the stuff I've written or the stuff I use to analyze all this communication, is running in the management, in the level 1 management domain. And the interesting part about this, there's all the boxes in gray, this is like user space code. So I don't modify the hypervisor in any way. Instead, I use hypervisor APIs and implement all this functionality as user space utilities. So how does this work? The level 0 hypervisor is Xen hypervisor, so we have a Xen API we can use. And implementing this in the level 1 user space has the important advantage that even if my code is shitty and crashes, which happens a lot, then we don't crash the whole system, so the hypervisor, the level 0 hypervisor will stay alive. So development is much easier than if you would modify directly the hypervisor itself. And to support this, so we have this virtual machine introspection library, and we use libvmi for this. And libvmi basically gives us access to this nested hypervisor. So the nested hypervisor is a virtual machine in itself, and libvmi gives us a way to access and manipulate all this guest state of this nested hypervisor. So we can look at the memory, we can look at the CPU registers. The cool thing about libvmi is that it's completely largely hypervisor agnostic. So in theory, you could support Xen or KVM as the level 0 hypervisor. And it's a user space API, so it's just a C API you can include in your tool, and then you can start playing around with the hypervisor. So it's not like any kernel components or something like that. And for us, most importantly, the Xen version, so our level 0 hypervisor is a Xen hypervisor, and the Xen version of libvmi supports a concept or a feature called memory events. And memory events basically gives us the feature to trap on access to a guest physical address. So we can say every time the guest, in this case the guest is still our nested hypervisor, accesses a certain physical address, we get a notification and our function gets called. And this is really easy. So the code on the left-hand side, basically we say, yeah, we are interested in this physical address, and we have these callback functions, and then we just register this, and every time we see memory access, we get the callback function. And this is implemented on top of extended page tables. Extended page tables are like the second layer of address translation, supported by hardware-assisted virtualization. So the idea is, if we register such a memory event, libvmi will simply disallow access to this guest physical address. So when the virtual machine accesses the guest physical address, it will trigger an EPT violation, which will trigger a VM exit, and the VM exit is then forwarded to our libvmi handler, where we can do whatever we want. And if you have this feature, then memory access tracing is actually not too difficult. So it's a 4-step approach, or 3 main steps. First of all, we want to find all shared memory pages. So we need to identify which shared memory pages are used for the virtualized device communication. Then we want to register our memory event handler. So this is the callback function that gets called whenever a memory access occurs. And in this callback function, we want to analyze every memory event. So every time this physical address is accessed, we want to look at the context and see and extract the information we later on need for our double fetch analysis. And then later on, we have this step where we actually search for double fetches, but the advantage of this is offline, and this can happen at a much later point in time. So the trace collector is the main component. It's actually the only component I've written by myself. And the core idea is we use libvmi to inspect the memory of the hypervisor, of the nested hypervisor, and identify all the shared memory pages. This is one of the code paths that's actually target specific. So as of now, I'm talking about Xen as the level 0 hypervisor, but in theory, the level 1 hypervisor can be any target. So you can use, or you can analyze KVM, or Xen, or Hyper-V, at least in theory. But the trace collector is the code, or the component that's target specific. Because of course you need to identify these data structures that are used by the virtualized device front-end and back-end to extract the addresses of the shared pages out of them. after you extracted it, you simply, for each memory page, you register your memory event handler, and then you have this callback handler. The callback handler is more or less the main function that does the main work. For example, it looks at the instructions that trigger this memory access using capstone, disassembles them, and extract information out of them. So this is like the control flow of this callback handler. So this is called every time a memory access to a shared memory page occurs. And then we have like code that's responsible for extracting domain ID. We only want to find vulnerabilities in the privileged backend components, so we are actually only interested in memory accesses that are performed by the privileged backend. So we check if it's a privileged domain. If that's the case, we extract the instruction pointer and the CR3, so the page table pointer. Look if we have ever seen this combination before. If that's the case, we just fetch our data from the instruction cache, otherwise we disassemble the instruction. This is of course the case because a single instruction will perform a memory access thousands of times, and we don't want to disassemble it every time. Instead we have this caching layer. And when we get this information, we just create like a trace entry and add it to our stream. Then we do a single step and continue from that. So we store our traces somewhere, and I already mentioned like just putting them into a text file or something doesn't really scale. So instead we have a couple, so we want our storage to be really fast. It should be persistent so we can do our analysis later on. And the performance is really important because this, if our trace storage is fast, we minimize our tracing overhead so the whole system goes a bit faster. And the coolest thing to have is if your traces are compressed in some kind of way. Because if you have compression, we can store long traces, so I can just activate tracing and let the virtual machine run for 2 weeks, and the trace won't be like terabytes in size. And interestingly, there's a tool that fulfills all these requirements. It's called Xenpwn. And Xenpwn isn't really well known in the security industry or like from security researchers, so I have a short slide introducing it here. It's an open source project by the operation system group at the Karlsruhe University. It's a German university. And Xenpwn is actually developed for full system memory tracing. So you boot up a virtual machine in QEMU or something, and you log every memory access, including the memory content that is performed by this virtual machine. So you can do this for performance reason or to do replaying of a whole virtual machine. And because it's like, so this is this requires much more performance than we require because we are only interested in shared memory accesses. So high performance is like one of the core features of Xenpwn. And it's implemented as a C++ daemon. It's simply running user space, and you get like a C library to talk to this daemon. The communication, funnily enough, is also implemented on top of shared memory pages. And then, if you write these trace entries, they are compressed, or they are compressed using a specialized compression algorithm. So the compression algorithm they use is actually optimized for memory traces. So this gives you high compression speed as well as really high compression rates. In practices turn out that like my memory traces, because the shared memory pages are almost like staying constant, I get like a compression rate around 90% out of that or something, so it's really impressive. Actually, I think this is a cool tool which can also be used for other stuff like heap visualization or something, so it's highly recommended and you might want to look at it. So these are like, what do I write into this trace storage? I have like trace entries, 2 different types of them. So we have, for every memory access, we have the entry shown on the left, which is 32 byte, and the main parts of that are simply, we have the instruction pointer, so this is like the instruction that accessed the memory, so it's an instruction somewhere in the backend component. We have the access memory address, and we see if it's a read or write instruction, so this is like hidden inside this tag field. And then, in theory, I could log what kind of data is written or fetched from the shared memory. I don't need that for my double fetch analysis, so the data field is just zeros. but this is extendable, so if you have like analysis where you need access to the memory content, you can use this as well. And then for every unique instruction, so for every like instruction that performed the memory access, we store a second trace entry, which just gives us like the instruction bytes, so we can later on disassemble it again and look at what kind of instruction it is, as well as the module name, so like the kernel module, where it's coming from. And then the actual double fetch algorithm is quite simple. So this is like a really simplified version. You have, it ignores like overlapping accesses as well as interweave to read and write accesses. But the core idea is you just iterate through the trace, and then you look if you see a read access to a certain address. If that's the case, you add the instruction pointer to a map or to a hash map. And at the end, you just look if you like find a map entry with more than one memory access. So it's quite simple. This is like 50 lines of C code if you have the API to talk to the trace storage. And you just let that run on your whole tracing stream or trace storage, and then the vulnerabilities should jump out to you. So the analysis step is quite easy, but if you do like the analysis or the tracing correctly, you will find vulnerabilities with this simple code. So it turns out this actually worked quite well, as we will see later on in the results. So the good thing about this whole architecture is you have a really low passive overhead, because it's just hardware-assisted virtualization, so it runs almost as fast as the native system. Most of the code is completely target independent, so you can analyze different hypervisors with that. You can also analyze something like the Chrome sandbox with it, because that would also uses shared memory. So every software that has a shared memory interface that's also a trust boundary can be in theory analyzed with that. And because everything is like user-based code, you can extend and develop it quite easily. Two main problems are the high active overhead. So when the shared memory page is actually used, for every memory access, we will trigger an VM exit. VM exits are expensive, so the performance, if you have like a lot of data pushed through the shared memory pages, starts to get kind of slow. So it's useful if you only want to trace accesses to some memory pages, but it won't be useful if you want to analyze like the whole system, every memory access that's performed by the whole system. And the main problem that turned out to be like kind of a shame, or that influenced my results quite a bit, is that we rely on nested virtualization. So nested virtualization means we need Xen to support a nested hypervisor running inside it. And nested virtualization on Xen is an interesting topic, because if you look at the Xen documentation, you will see that they say, yeah, it's considered a tech preview, and it should work reliably in most cases. So it's kind of, you shouldn't do this in production, but it should work. It turns out that's actually not the case at all. So Xen on Xen works very well. KVM on Xen, so running KVM nested in Xen, works most of the time. And Hyper-V on Xen, which was actually one of my main targets when I did this work, doesn't work at all, so you can't boot up Hyper-V as a nested VM in Xen. For this reason, all of the results that I present in the next slides will be Xen vulnerabilities. But interestingly, Hyper-V, the next version of Hyper-V that will be released with Server 2016, should support nested virtualization. So I'm quite hopeful that I can use this to run Hyper-V under this whole tracing tool to potentially find some interesting bugs in that as well. So to the results. I basically did two tracing runs, one on a Xenpwn system that runs at that point in time the newest version of the Xen hypervisor, so Xen 4.5, and then you have a Xen SUSE Linux enterprise system that runs Xen 4.4. The reason for that, why I have like these two different target systems, is simply they use a different management stack from Xen, and this XL stack and the Xen D stack. And this means a different support for para-virtualized devices. So there are some para-virtualized devices that are only supported under the older Xen version. It turns out the main problem of this whole stuff is basically getting good coverage. So it's dynamic analysis, and I don't have an automated way to exercise this functionality of these para-virtualized devices. So instead I manually trigger device activity or like do some kind of scripting that triggers a lot of different disk accesses and stuff. So this is something you probably need to work on to find more bugs. And in the following I only show bugs that are found with default compilers. As it turns out, if you compile without any optimization, you will find a lot of these double fetch bugs. And when we reported these results to the Xen developers, they also patched like a lot of bugs that could be vulnerable in theory, but aren't vulnerable in praxis. So I'll just talk about bugs that actually exist in the real world. So if you read my full thesis, you will find a lot of more details about like the different instruction types and attack surface and so on and so on. So the first thing I found, and this is like interesting because it's not really exploitable due to compiler optimizations, is in the Xen disk backend that's included in QEMU. So this is the disk backend. If you just use Xen and your virtual Xen machine just has like a single file as a virtual disk, this is implemented in QEMU code. And as you can see, the lines highlighted with the arrow, we basically have this source pointer that points to a shared memory section, and the number of segments is simply a variable inside this shared memory page. And the access is like over there, and then you have this interesting if condition. And as you can see, they look that n, which is defined to block interface max segments per request, is larger than this number of segments variable. If that is the case, so if there's like a maximum, then they set n to this number of segment variable. And you can imagine if you can flip the value of number segments between these two lines, so between the if condition and like the actual assignment, you have a trivial heap-based overflow down there, because then you can simply like iterate an arbitrary number of times in this for loop. As it turns out, this is actually not exploitable because every compiler, if you have like optimization enabled, will transfer these two lines into a single memory access. So my tool discovered this vulnerability on this code area because of this access like on the top. So you have this access and this access, which is like two memory accesses. But because the assignment on the top isn't actually security relevant, this is not like an exploitable bug. But it's interesting because it shows that developed this code never even thought about double fetch vulnerabilities. Otherwise, you would never write code like this in like for a security critical length check. So the next bug, and this one is, I think if you want to like do real world exploitation with these vulnerabilities, this is probably the most critical one. So again, you have like these segments array, and segments array is stored in a shared memory area. And what happens here is these are like, so you send like a request over the disk backend, so you specify this is like the first sector I want to read, and this is like the last sector I want to read or write, depending on the request. And they calculate the number of sectors over here. And after they calculated it, they access the memory a second time, like this last sector and first sector variable, to check that the number of sectors you're actually accessing doesn't need more than a single memory page of space. Because all the other code expects basically this request to only require so many sectors that they still fit into a single memory page. Because you can simply flip the value of last sec and first sec in between these two accesses, you can trigger an out-of-bound read when you are writing to disk, and an out-of-bound write when you are reading from a para-virtualized disk. So this is kind of an interesting bug, and is probably exploitable. However, there's one bug I found much more interesting, even if it doesn't have that much practical implications, because it's in the PCI back para-virtualized device backend. So this bug is only exploitable if your virtual machine has like a PCI device, which turns out to be the case if you have like a GPU inside your virtual machine, or like a special network card, but is not the case for like most server environments. So the vulnerable code is shown on the left, and it's kind of interesting. So it's the Xen PCI back do op function, and it's a switch. And so it doesn't look vulnerable at all, at least from my perspective. You can see it's switching over this op CMD value, and again, op is a pointer into shared memory. And so this doesn't look vulnerable, but but my tool basically gave me that location as a potential double fetch. And if you look at the code, you can see that this is actually quite interesting vulnerability. So the switch statement is compiled into a jump table, which is like the typical compiler optimizations to optimize like switch statements with a lot of cases. And if you look at line 1, they access this memory address at offset 4 from the R13 register. R13 points to the shared memory location. So this is like the op variable in our source code. They compare this value with 5, which is like the upper limit of the switch cases. And if it's larger, they jump to the default case and just execute this default case. But if at this point in time the value is smaller than 5, they jump into line 4. And line 4 is really interesting because they access the memory location the second time and then directly use it as the destination of an indirect jump. So you can see we read the value from the memory location the second time, put in an EAX, and then use RAX multiplied by 8 to jump to a certain offset in this jump table. So this means if you can flip the value between the first line and the fourth line, then we bypass this range check that's inserted by the compiler and can jump to more or less arbitrary location. This is interesting because it's a valid compiler optimization. So the bug actually is that this op CMD or the op pointer isn't marked as volatile, so the compiler doesn't expect it to change in between two memory accesses. But it gives you like indirect control over the instruction pointer and is more or less completely hidden from source code. So this is a bug I wouldn't discover while doing source code auditing, at least not before I saw it in this case. So how to exploit this? It turns out to be the race is really small, so it's just like these two instructions. You have this move instructions and this jump, this conditional jump instruction. But if you have a guest virtual machine that has more than one core, it can be trivially wrong. And the good thing about if you lose the race, it will simply jump into the default case. So you have like infinite retries to win the race. And you can simply trigger it by sending a PCI request and flipping this value, this op CMD value, using the XOR instruction. So you can see this is basically the assembler code my exploit uses to just flip the value at the location, the RAX register points to 225, which, as we will see later on, helps us to gain code execution. So the problem is we don't get like direct instruction pointer control because it's an indirect jump. So we need to find a reliable offset that points to a function pointer we can use. Normally on all systems I looked at, this PCI back module is actually a kernel module, so it's not compiled into the kernel. So we can't be really sure about its address, even if we know like the base address of the kernel. The virtual address of the backend mapping is also not known because this is like a randomly allocated memory location. So it's a lot of, or it's very similar to a remote kernel exploit from the whole like conditions you have to exploit this. My approach to exploit this is to trigger a type confusion, then we get like a write primitive out of that, and we use this write primitive to get full code execution. So it turns out to be the case that there's a second jump table that's generated inside the PCI back module, and it's generated for this send PCI back front and changed function, and it's almost directly behind the jump table that was generated for our vulnerable function. So that's the case. That's the reason why I can simply put like 25 into this and jump into this jump table. And if you look at the send bus state initialized case, this uses the value of the R13 register as the first argument. So this is the code for this case. we push or we move R13 to the RDI register and then call Xenpwn back attach function. This should be a pointer to Xenpwn back device structure, but it is a pointer to the start of our shared memory page. So the value at this address is completely under our control. And if you look at the Xenpwn back device, which is shown like on the left-hand side, you can see that it contains a mutex. So the mutex is called devlog, and the first thing that the Xenpwn back attach function tries to do is log that mutex. So we can now call mutex log with a fake mutex structure that's completely under control. So when I first saw this code, I thought, yeah, mutex log is probably not too interesting. It will just flip like an integer or something. But it turns out mutex log actually does a lot of stuff. So it has a fast path. If the log count is simply 1, it will simply flip to 0 and then execution continues. But if the log count is unequal to 1, then the slow path is triggered. And the slow path does a lot of more stuff that we can use to get a right primitive. So we want to reach this code path that calls list at tail, so it works with a linked list. To do this, we have to bypass the mutex optimistic spin function, which is quite easy. If then the log count is still not 1, so it will repeatedly check for the log count, they create a mutex waiter structure on the stack, and this is added to the wait list of this mutex log. The idea is you add yourself to the wait list, and then your kernel thread goes to sleep, and if someone else unlocks this mutex, your kernel thread will be woken up because it's the first component in this wait list. However, because we completely control this wait list pointer, we can write this pointer value to this waiter structure that's stored on stack to an attacker-controlled location. So this is the right where, but not a right what. So we can write at an arbitrary location, but we can't like directly choose the value we write. Instead, we write a pointer to attacker-controlled data. So it's kind of a ugly primitive because we can't simply like override a function pointer or like a function table or something. And the main problem to make this like a really stable exploit is that it's one shot. So we can trigger this override once, then the PCI back module will hang because the function didn't return, so we can't like execute this override multiple times. It turns out that it's still exploitable in a lot of cases. If we know the kernel version, or like have an info leak that gives us the kernel version, and the target kernel doesn't have KRSLL. So this might be a problem for some cases. If you want to target something like cubes, for example, you probably have the same kernel version in your virtual machine than you have on the host system. So in that case, it would be quite easy to exploit. So the exploit I present like requires you to know the kernel of your target system. If that's the case, you just have to find like one global linked list where you can add our faked entry to. And the idea is you have this linked list as the Linux data structure. It's simply like a double linked list which is used all over the place in the Linux kernel. So you have this next pointers and the previous pointers that point backwards. We construct our data structure in a way that we have this fake previous pointer. So this is this wait log fake previous pointer that points to the list head, and after we trigger the mutex log function, this whole stuff looks something like this. So we can see list head next points to the waiter structure points to our control data. It's important to know that we don't really control the data stored in this waiter structure. So we have like a linked list, but it still contains one junk entry, which might be a problem in many cases. So we need to find like a good override target that has to fulfill some prerequisites. First of all, it needs to be a global data structure, so it can't be simply something with a random address. It shouldn't be like manipulated during runtime because we don't override the previous pointer, our elements would be simply like removed from the list again. And most importantly, the code using this linked list needs to survive one junk entry. We don't have complete control over this data structure that's stored in our stack frame. So it would be stupid if this just like dereferences a pointer in the data structure and crashes or something like that. It turns out to be the case that there is actually a cool linked list that we can override that's also used all the time, and it's defined in this exec.c source code, which looks like it's still like in the original shape from the 90s. And it's the formats linked list. And formats is basically used whenever you call exec. The Linux kernel supports different file formats. So you can like have normally, you will have an ELF binary, you might have a shell script, or you have like some stuff like this old a.out font. And whenever like exec is called to execute an input file, this formats linked list will be borked to call this input file. And so we can see we have this function to walk over the formats list. It executes the try module get function on the format module entry, and if that succeeds, then we see we have this pointer to load binary that's called. The good thing is that for our data entry, the try module get function fails, so this function pointer is never dereferenced. Instead, we have a fail in the try module get function, and it simply walks to the next entry, which is completely our own control. And then getting code execution out of that is quite trivial. We simply set the address of load binary pointer to a stack pivot, so we can jump into a rob chain. And the rob chain allocates execute memory in kernel context and copies the shellcode. So it just calls vm allocate exec and then a mem copy to copy our shellcode into this new location. It's actually quite a long rob chain. If you ever did like Linux kernel rob, you have like infinite gadgets, so it's quite easy to do. And after we did this, we restore like the original formats list, so exec works again. And when an exec call triggers our, or after we restored the original formats list, we just execute our shellcode and then return to user space. And the cool part about this is, so this whole code, the load binary pointer will trigger whenever the management domain or the host system executes any binary. So every time an exec is called on the Linux system. And this will happen sooner or later. So we are quite sure this code execution will trigger after a short time frame. So I have a demo for that. So we can see I have like two shell connections to the guest system. So on the left-hand side, on the right-hand side. The idea is we use the ls-PCI command to trigger PCI activity, so we would see like the para-virtualized device. While on the left-hand side, I'll try to trigger the race condition. So this is like the code that retries to trigger the race condition until we override the value and win the double fetch race. So we start this iteration, and we can see at the first time this ls-PCI utility just returns and shows like the ls-PCI value, but now it hangs, which shows we have won the race. And we wait until the function returns, or the comment returns, because then we know nobody else is writing in our shared memory region, and then we trigger our second tool, which will override the formats list and trigger the execution of our shellcode. Before we do that, we open a netcat connection on 1, 2, 3, 4 and wait for the reverse connection. And if we see the command, we can see we get a root shell, and the root shell is running on the Xen host. So this is like a full Xen breakout where we go from the unprivileged domain to the .management domain and have full code execution on the host system. Okay, so that's almost everything. I just, if the slides are coming back up, here they are. Yeah, so as I already told you, this is actually part of my master thesis. And if you want to learn more about the Xenpwn stuff, this is described in much greater detail in the actual thesis. It doesn't include the exploit stuff, because this is something I actually did after I finished the thesis. So I'll release the exploit code for the PCI back vulnerability, as well as a white paper describing this format sway or this type confusion attack somewhere after Infiltrate, probably next week when I'm back in Germany. And I plan to open source Xenpwn completely sometime next month. The main problem is currently only building on my machine, so I have to clean that up. And if that's done, I can release it as open source. So future work, I would really like to use Xenpwn against Hyper-V and VMware. This requires improved support for nested virtualization, which will probably or hopefully happen in the next month. And it might be interesting to use the same approach to analyze other shared memory trust boundaries. So an important or a prominent example of that is Sandbox. And then there's the open question, what type of bugs can we find if we actually use full memory traces? So of course you could use for structure padding leaks or something like that. So I have a couple of ideas of interesting vulnerabilities you could find if you start doing memory traces that also trace the memory contents. Okay, that's from my side. Thanks for your attention and happy to answer every question you have.